Hey, I'm Adarsh Patel, and I'm in lab section MO3 from Tuesdays 12 to 3 p.m. And for my lab 1, constant velocity motion, I observed a 2012 Mustang moving along at a constant velocity. And in the main conclusion I came to was that at constant velocity, an object is neither speeding up nor slowing down, and as a result, the acceleration is zero. This would make the F-net equal to zero.
Into the coordinate axis, so the positive x direction would be along this line right here, and the car would be moving along the positive x-axis. As for the initial location of the car, I decided to use the middle of the back wheel as my starting point. So the initial location was at the origin, which would be 0, 0, and the average location throughout the video clip was the middle of the back wheel, the red dot right here. And I started observing the motion of the car when the back wheel came into the video, and I observed it until the back wheel was out of the video. As you guys can see from this clip right here, all the red dots are the average location, and I observed it until it was out of the view. As for my calibration stick, I decided to use the diameter of the back wheel, which I found online, as 0.457 meters, and that was the scale length for my whole video. The whole video clip was 0.633 seconds, and the time between each frame was 0.033 seconds.
To set some initial conditions, I found the mass of a 2012 Mustang on the internet, which was 1,714.58 kilograms, and as I mentioned before, the initial X location of my car was at the origin, so 0 meters, and to find the initial velocity of the car, I took delta X divided by delta T. After analyzing my tracker data, I found the final location of my car to be 4.758 meters and subtracted it from the initial, which was 0 meters, and the total length of the video was 0.633 seconds. And after dividing 4.758 by 0.633, I found the initial velocity to be 7.517 meters per second.
After setting some initial conditions, the mass of the car, the position of the car, and the velocity of the car, I picked my delta t to be 0.05 seconds, which is very small compared to my whole length of the clip, which was 0.64 second. As you guys can see, the F-net vector is 0, 0, 0, as I mentioned earlier, since the car is moving at a constant velocity. And using Newton's second law, I predicted the final velocity of the car. Car's final velocity equals car's initial velocity plus F-net divided by the mass times delta t. And since F-net vector is 0, 0, 0, this whole term is 0, which means that the final velocity of the car is equal to the initial velocity of the car. As for car's final position goes, I said car's final position is equal to car's initial position plus velocity times delta t. When I start my model, this is what I get. The car starts at the origin and moves along the positive x-axis. As you can see from the graph starts at 0, 0 and moves along the positive x-axis.
So when comparing the tracker data with the model data, this is the graph that I found using the tracker data, whereas this graph right here was the graph I found using the model data. The x-axis is the time in seconds, and then the y-axis is the horizontal distance the car moved in meters. As you guys can see, the model depicts the tracker data very similarly. For what if I consider the velocity not being constant and the F-net vector not being equal to 0, 0, 0.
So to test my new model, I changed the F-net vector to 30,000, 20,000, and 0. New model. The object moves along a parabolic path instead of a straight line, and the car does start at 0, 0 again, but the final position is farther when the net force is not 0, 0, 0.
What it all means, at constant velocity, F-net vector is equal to 0, 0, 0, and then the final velocity is equal to the initial velocity by this equation, as you guys can see right there.
When Fnet is equal to 0, Fnet divided by the mass term becomes 0, so final velocity equals initial velocity. As with most real-life situations, the velocity isn't going to be constant, and the Fnet vector is not going to be 0, 0, 0. So in the case that happens and you wanted to find the final velocity, you guys would use this equation right here and plug your Fnet vector in right here, and then you can simplify to get the final velocity vector.